So anyway, it's a very tough course, tough test. So they're here to talk about the CubeSat, the satellite that we basically saw the news about it in an Empire news section of the Press Democrat. They have been working on it for about 3 to 4 years, 2009, right?
No, we were working on it since May. I walked out of my finals class in May this last year.
Okay.
So we built the whole satellite in about 3 months.
Isn't it amazing? So they're going to talk about the whole process and most of the stuff that I'm not even aware of, so probably any new for me too.
Yeah.
I'll let them introduce themselves a bit more in detail if they want to tell you their experience at Sonoma State, stuff like that. And if you have any question, please don't hesitate to ask. Do you want to interrupt you or?
Yeah, just go ahead and interrupt.
Okay.
Because I'll probably just start. You guys don't keep me online.
Okay. You want the lights off or?
You guys can see that, right? Yeah.
Okay, great.
So my name is Kevin Zach. I'm an SPS officer at Sonoma State University. I'm the outreach officer. So another reason why I'm here is because it's part of my job description, I guess. And we came here for the APS conference. I don't know if you guys remember that or not, recruiting. I know Daniel came. And Hunter.
Oh yeah, so I'm also an SSU student. I did come here also. As Ina said, I'm the webmaster of the SPS club, and I also was involved in the satellite project, not nearly as much as Kevin, but I was technically involved.
So to start off with, if you watch this video, the only reason why I'm just starting with this is because it just starts to play. It's actually running. This is a video image of Russia, where the rocket launch launched our satellite up on November 21st. And so in a little bit, you'll actually see the rocket come out of the ground. It kind of reminds me of like one of the nukes going off from Russia. And so I think they just kind of like took the nuclear payload off. There you go. And you see it just kind of, there it goes. So that's on November 21st, right around noon in Russia, so midnight here. We're exactly 12 hours away from that. The satellite went up. And the reason why they put it up on the noon line is to make it sun synchronous. And so you guys have all done orbits equations and stuff like that. You guys started doing that?
You did not get
You didn't get to the section. Oh, that's nice. Okay. So basically, when the satellite is going around the Earth, it's in a plane, and then the Earth rotates around it. Well, this particular launch made it so that the plane of the orbit is constantly pointing at the sun. So as we go around, it's always looking at the sun. And so the satellite comes over noon and midnight everything here. And it goes around the Earth 14.95 times a day, and it takes about 99 minutes to go around once. So it's moving pretty fast, and I can show you a program a little bit that actually tracks the satellite. So backing up a little bit too, because I was just, I can't stop it. So this is the satellite, not actual size. The satellite is 5 by 5 by 15 centimeters, or 2 by 2 by 6 inches, to give you an idea. We started building it in May of 2013, so it's still this year, when we started prototyping and designing it. The satellite was completely designed at Sonoma State, and all the boards, circuit boards and everything inside of it were etched at Sonoma State in-house. And so that was part of the problems when we first started this. Everybody at Sonoma State knew how to do the big components. I don't know if you've ever seen electrical components before, but they had the legs and they look like bugs. You seen those before? So yeah, the discrete components. And so that was all we knew how to do. And so when I started designing the satellite with those components, it didn't work. It was huge. And so we had to pioneer at Sonoma State surface mount soldering to shrink everything down. And I have a picture of the surface mount stuff a bit later. So this is the satellite. So you can see these antennae here. This is because physics 40. You haven't done frequency. So in 41, you'll learn about wavelengths and stuff like that. And so the 433 megahertz band that we operate and communicate with the satellite in is about 70 centimeters. And so this is a quarter wave dipole. And so this is like 14 centimeters. So you have 14. And these are the very ridiculously high efficiency solar panels. I don't know if you've heard in the news, just recently they broke the record of being at 44% efficient. These solar panels are 40% efficient. And so the reason why is because the connection to Morehead State, or as the newspaper likes to say, Morehouse State, because they got their name wrong. There's a guy named Professor Bob Twiggs that was a instructor at Stanford, and he thought of the whole CubeSat pocket cube design. He kind of invented the whole idea. So everybody else is going bigger. It's like, let's go smaller. And so he's really famous in the aerospace world. And so people just give him free stuff. And so these were little triangles of solar panels off of some really probably $1 billion NASA satellite that got trimmed off, and they had them and they just gave it to him. And so those solar panels are probably worth like $5,000 a piece. But, you know, didn't know that when we were handling it, and we were just handling it with our hands and doing something like, oh crap, we chipped it. I mean, we weren't that bad, but it was still like, we found like a chip once. So that was really bad. But we can also communicate with it. This pin connector is obviously not for onboard space. This had the ability so that we could actually reprogram the satellite without going over the radio, charge it, and look at all the different status of the satellite. And so we did extensive testing at Snow State. The reason why I'm kind of telling us all this too is because there are potential opportunities for you guys to work on the next one. So I'm just kind of giving you a broad overview. So the connector here, you can see, and you can see this little flange is a little bit further out on this, is because there's something called the Mr. Pod. Well, I don't remember what it stands for, but it's kind of like a jack-in-the-box. And so this satellite, the antenna's folded down, and that's why they look kind of funny. If you've ever played with a tape measure before, you can see that it bends in one direction. That's basically what that is. It's a spring steel tape measure without the paint. Cut, trimmed to be resonant at the right frequency. And so it folds over along the body, and this whole thing slides in a jack-in-the-box tube with a big spring on it. And you, when it pushes down, there's a trap door with a nichrome wire, and that's a wire that when you heat up, it melts and then the whole thing gets sprung out. And so we were part of a group on a satellite called UNISAT 5, which was an Italian-built satellite. And so we were actually technically, I think, one of the first tertiary payloads. And so basically the whole CubeSat thing goes, you have some primary mission, that's this big business that has their primary, that pays for the entire launch. And instead of having ballast, which is just weights in the rocket, to balance everything, they stick us in there. And so we basically hitch a ride to space. And so the main fairing comes off, they launch the primary mission. A couple hours later, because they don't want us interfering with their stuff, we get launched out. Well, this time, a satellite called UNISAT 5, which was a microsatellite, launched out, and then an hour later they launched us out. And so we actually hitched a ride on another satellite, which was kind of weird. But given our size, it kind of made sense. And it actually launched out some other, like 4 pocket cubes and 2 1Us or something like that. So this is a pocket cube. Unit size of 5 by 5 by 5 centimeters. So this is a 3P because it's 5 by 5 by 15. And then the other thing I'm saying is CubeSat. So our 1Us is the unit size, which is 10 by 10 by 10 centimeters. So if it's 10 by 10 by 10, it's a 1U. If it's 10 by 10 by 20, it's a 2U. So that makes sense. Let's see, I'm rambling. So anyway, so that's how we got launched out. And we actually, one of the things that's not shown on here is we actually have these really large Cap-1 sails on our antenna, which are fairly see-through and UV resistant. We had to design them because this satellite is at close to 700 kilometers. And 1996-ish, there was an international treaty about space junk, where you have to come down within 25 years or have a propulsion system to either put you into the boneyard or deorbit you. And because of our cross-sectional area, we have very low drag coefficient. And so it takes a long time for us to come down. So in this particular state, the simulation showed that we're going to be up there for 29 years, which was a violation of international law. And so we basically built these large sails on it to give ourselves a larger cross-sectional area, because it is 700 kilometers up, but there are still particles from the sun in the atmosphere and stuff like that. The Van Allen belts are flying through, and so the sun does a big coronal mass ejection and charges the atmosphere. We're kind of more drag coefficient. It's kind of hard to calculate exactly because it's so variable, the drag coefficient. anyway, so we have these large scales, and that kind of saved us. It got us down to about 19 to 24 years, so we were good. So the thing will be flying for 19 to 20 years. So on it, this is the whole SSU team. I didn't let my advisor know, but I etched all of our names in the board because it's inside the satellite and no one knows. I figured it was safe because the Morehead State had their name on the solar panels because they designed the solar panels and then I had to fix them. So anyways, this is something called a torque coil. So you'll learn in physics 43, your E&M class, that if you have a coil of wire and you put a current through it, it creates a magnetic field. That's 42, sorry, 43 is more. 42. And so just like the way the compass wants to align with the magnetic field of the Earth, when you put a current through this and it makes a magnetic field in the spacecraft, the satellite wants to align with the Earth's magnetic field. And so we can actually use this to point the satellite. We haven't done this portion of the mission yet, but everything's there and we're working on some simulation programs. And so it's another one of those things that you might be able to work on. I'll get to that later. And so if you think about it, as you go over the poles, the magnetic field is constantly changing as it goes over. It changes like every 5 minutes on orbit, but then over the poles are rapidly changes and flips direction. So if you pick your opportunity right when to turn it on, you can basically do something called magnetic sailing and point anywhere in the sky. And because it's, this is the insides of the satellite. You can see the connector I was talking about before, the torque coil. This right here is the radio. It's an $11 radio from SparkFun. So I don't know if any of you guys have done anything with microcontrollers or anything like that, but the whole maker movement. That radio is literally $11. On the ground, it only goes about 300 to 600 feet. It operates at 100 milliwatts. Your cell phone's about 400 milliwatts of power. So it's 4 times less powerful than your cell phone. So it's closer to a house cordless phone. And we talk to it 700 kilometers up into space, which is pretty cool. And we've closed the link and been with 2 of those radios, and we can actually just spits out data packets. Which brings me to the next point. Today around 11 o'clock, we're actually having a pass over Sonoma County, which is pretty high. Yeah.
Very quick question. How did you extend the range of that? What did you do to extend the range from 300 feet to several?
Really good line of sight because it's up. There's no ground effects.
No session.
We did actually yesterday. That's why I got scratched. We raised a 20-foot mast with we have basically a pointing system with Yagi antennas. I don't know if you've ever seen on people's houses that big aerials that are looking in one direction, the directional antennas. We track it as it goes over the sky. So, but today at 11 o'clock we're having a pass over Sonoma County. And so I'm going to try to BNC into our machines that are running everything, and so we can actually see a live pass if you want, and we can see the waterfall plots, you can see the signal coming in, and you can see the data popping out. And the guy that I'm working with, Dr. Garrett Jernigan, who is a principal scientist at Berkeley forever, he's going to be actually commanding it. So you'll see, which I'll get to the plots of what it looks like. You'll see a big old whiteout. Actually, I have a picture of that. We'll get to it. Sorry. So anyway, just finishing this up here. So we also have something here. This is a magnetometer, and it measures the Earth's magnetic field. It's a little bit different from the magnetometer in your cell phone, which uses a Hall effect sensor, which you'll learn about when we're doing the calculations in here. This one is an induction one, so when you get to physics 42, you're going to do an experiment where you're looking at resonant frequencies with a capacitor and an L or LC circuit, and it basically sweeps through the frequency and it finds the magnetic field based on the coils. You can see the black thing is actually coils in all different directions, and it's an XYZ magnetometer. And so this is the example of the circuit. This chip right here is a 1/2 inch by 1/2 inch and has 64 legs. And so that's how small we started getting it down. Before we started, and this is a standard kit right here. This is only 5 legs across. So you can see how much smaller we can get. So this whole thing was built in-house. So this is an example of real flight data. There's different packets that the satellite autonomously sends every 20 seconds. It sends checksum packets, which basically checks the code. So if you see these two numbers are the same, and these two numbers are the same, we're good. Because what happens on orbit, you have this program in memory, and a cosmic ray will come in and it'll hit a bit and it'll flip the sign, or it'll flip the bit from a 1 to a 0, or it'll just completely destroy the transistor. That's the worst case. But so it can flip the bit, which basically will make it so that the program on orbit is wrong. So we have to be a little careful. Radiation is what's going to kill us. And so it may be physically up there for 19 years, but it won't be operational for 19 years. It's going to be either dead today or to 10 years from now. It's a completely random chance of when the radiation is going to kill us. So, because we're flying through the Van Allen belts. Do you guys know what the Van Allen belts are? Aurora Borealis, have you ever heard of those? Basically the sun, a lot of particles gets trapped in a magnetic field. When they dip low enough to go into our atmosphere, it ionizes and makes the pretty lights. And so, yeah. And then the beacon packets, I know these are just numbers to you, but you can see that we've reset the satellite 325 times. This is how long it's been running since the start, so it's been running this times 10 seconds since it's been reset. This is the battery voltage. So this is 4.3 volts is the battery voltage of the satellite. These are 4 solar panels. And so you can see at 4.5, 2.9, this is dark side, this is away from the sun, 4.4 and 4.5, which is strange is the 4.5 and 4.5, the orientation of the satellite is probably at an angle to the sun. But what's neat is that we actually get 20% of our power from the reflection of the Earth. So the sun reflects off our atmosphere, and that's why this third solar panel is lit at a little lower voltage. Even though, yeah. And then these 3 temperatures that are in Kelvin, so 275, 270, so it's just below freezing point, so it's kind of neat. Space, I don't know if Earth is like 2 Kelvin, but what's interesting is we're really worried about the things melting on orbit, because unlike on Earth, we have convection and conduction to be able to get rid of heat. In space, you only have radiation, which is one of the least efficient ways to do it. And so any of the components inside that are charging and solar panels, stuff like that, creates heat. It's really hard to get rid of because it's got to literally radiate black body radiation out. And so we're really happy that these numbers are low, or they're actually in a really nice range. They're like optimal, it's right around 270 Kelvin, which is 273 is freezing. I'll go back. Sorry. And then just this. There's the magnetometer readings, so it's actually measuring the Earth's magnetic field. And with these 3 points, we can actually know exactly where the satellite's pointing, because the NASA's really figured out our magnetic field and have this huge, 100 expansion equation for it. And so, since we know roughly where it is overhead, we can actually place it exactly where it's pointing with those numbers. And that's one of the programs that we're running right now that you guys can do. And then this number right here, 2285, it's actually telling us that the satellite spinning the precession around here is 22 seconds. So the satellite spins once every 22 seconds. And it does something called a fast Fourier transform on orbit. I don't know how far you guys in math is, probably not. You'll get to Fourier transforms and stuff like that in your future stuff, and we'll find the different periods of the satellite. So anyways, that's the real flight data, which you guys will see if you stick around. This is the first time we saw the satellite, and so this is frequency versus time, so it's like time versus inverse time. Graph, and see these little dots right here that are different colors. This is our satellite that we actually see. And we got our first data from it. And so the spread here is because the way we communicate, said it actually looks like a double peak, and each peak represents a 1 or a 0, basically, roughly. And so it goes back and forth. You can't tell on this because the time sample is too fast. One of those little whops is like a second. It takes about a second because we're operating at 500 baud. I don't know how many people are alive when they have dial-up. You guys have dial-up? 28K or 56K? We're at 500. So that's how fast we communicate with the satellite. But that's one of the rare things about the satellite. Everybody else tries to run it at these high baud rates, and we're like, no, let's go as low as we can. We want it to do 1 baud, 1 bit a second, because it's really easy to see, and I'll show you a picture. later of the actual bits, you can actually see, you can count the ones and zeros on it. And so that's how we got over the whole power issue, is that we spread out our peaks, because usually they're really crammed together, so as it goes through with the noise, you can't differentiate between the ones and zeros on these big satellites. And so even if they're spraying out a watt, sometimes it's pretty hard to see. And so the other thing to notice is that you see this, how it's the line here. Did you guys go over Doppler shift? That's 41. So I keep forgetting. So anyway, there's something called Doppler shift. So if you've ever had like a siren coming towards you and then it leaves you and it goes wee, like a train whistle, do you know what I'm talking about? That's what's happening to the frequency. And so as the satellite's flying overhead, it's sending us everything out. And as it's coming towards us, it's blue shifted. As it's leaving, it's red shifted. And so it actually changes frequency over its center frequency. So if this was on the ground, they would look just, they'd be in a perfect vertical line. But so since it's moving, it's slanted. And what's cool with this data here is you can actually calculate how fast the satellite's going. And there's a lot of information you can get from this data right here. And you can see there's another satellite right there. And so when you're watching these for hours, when we first did this noise going on the screen, and you saw two dots, or a dot, and then you like a 20, usually beacon packets are every 20 seconds, not standard, but just people do it that way. And you see it shifted over a little bit at that slant, you know that you start to see a satellite. And so that's how we first found our group. Because most people, we saw our satellites as we were talking to it a week and a half before most people were. Yeah.
So is your incoming bit stream, is it just like 1 0 1 1 0 0
Yeah.
from the? So how do you tell like 3 ones in a row from 4 ones in a row if the timing is being messed with from the Doppler shift?
The difference in Doppler shift between these points are pretty minuscule compared to the 500 baud. That's one of the really nice things about going to 500 baud, is because each bit is like 2 milliseconds. And so the Doppler shift here is not going to be changing by that
So
much.
you just have a fixed frequency and you know you can tell where the bits are.
Yeah. The other thing is these two peaks are going to be Doppler shifted exactly the same. And so if you reference off each other, that's the other one of the other ways you can do it. So the bit length isn't going to change, so that's what I should have said. So between the ones and the zeros, you go 0 0 0. The bit length doesn't change the Doppler shift. It's just what frequency you're looking at shifting.
Okay.
Does that make sense?
Yeah.
Yeah. Yeah. Yeah. What are these things? So this here is a picture of a data bump where we commanded it. So you see this really, really bright thing? This is what the satellite looks like when it's on ground. And we told it to do something called dump beacons, which is a command that the satellite, every 6 minutes, it takes one of these beacon packets that it sends down, which is instantaneous data that's out, basically the health and everything in satellite, and stores it into memory. And that does 3 hours of data. And so what we can do is when we give the command dump beacons, it will give us that data, and we have basically 2 complete orbits worth of data. And so from that data, you can see the night and day cycles, because it's an hour in the day and 30 minutes in the night, because it's so far away from the Earth, unlike us, which is like roughly 50-50. And also we can start to map out the magnetometer and what the plane of the orbit is and stuff like that. And what's neat is that you can see how it gets bright and then dim and then bright and then dim. This is about 10 seconds. That's because the phase of the antenna, it's that 20-second period. And so if you have 2 dipole antennas and they're perfectly aligned with each other, they have the best signal across. But if you put them at perpendicular to each other, you have a dB loss. You'll still be able to communicate, but there's a loss, and you actually see it in signal strength. And so it's another verification that our stuff on orbits work. So that's cool. All right. And this is what I was talking about with the ones and zeros. And so you can actually see this is like 1 0 1 0, and then down here 1 0 0 1 0 1 0 1 1. So that's actually the raw data that we can see. So we take data 2 different ways. One is something radio called upbeat. We call it B100. It's a brand, which basically takes a sample of all the frequencies, and then we can use an algorithm to pull out our data. And the other way is to literally hook up an exact copy of the ground radio on the ground, and it automatically just spits out the data and takes care of all the Doppler shifts and stuff like that for us, which we're ridiculously shocked that it worked, because it's a $11 radio. We thought we were going to need this really big ground stuff and do really hard picking out the data, and it's clear. I mean, it's kind of crazy. Other data would look like this, where you have like, you might have one here or another one here, and it more looks like noise, and you're staring at the noise trying to find it. If it's a weak satellite, that's what we thought we were going to have to do, but it just blaring through. I think that's the game. That's it. Does anybody have any questions?
You mentioned there's opportunities for us to actually work on this stuff.
Yeah.
We
So there's two different ways that you can go about. One is you can transfer to Snow State. There's my pitch for that. The other thing is, there is already a JC student, I can't remember what his name is, that's actually going to be working on some of these projects. If you talk to, probably email Lynn Kaminsky, I think is who, so I can give the email address to Jonas. And basically, if you want to, there's a ridiculous amount of projects. One of the main projects we want to do for an outreach is design a really cheap Yagi antenna. We're not buying it, we want to build it, and a preamp, and give them a box. High schools around the world a box, and they just point it straight up, and when it flies to the beam, we get the data, and it automatically sends. And so there's a whole project to build a Yagi antenna with for around $20, and so that's a really good engineering.
Garrett's under there.
The antenna under 20 is
Oh,
the Yagi. The whole project, we want to make it under $100 so that we can give it to high school students. They don't have to track; they just point straight up, and so it'll fly over every once in a while and get data. And so it's really kind of a neat engineering project. There's tons of information about Yagis online and stuff like that. And so that's an example of a project. If you're computer savvy, there's a lot of simulation programs need to be done. We need to analyze the magnetometer data to actually figure out where it's pointing, so that when we turn on the torque coil and it changes where it's pointing, we can actually tell that it changed, right? And I don't know, he probably has about 15 different projects, and he has more projects than there are physics students at Snow State in his head. So that's where, like, if there's projects that you guys would want to start to like try to work on, and they'd all be pretty much, as Garrett puts it, in the non-critical path. And so we're building the next satellite. We've actually already started. We're going to be flying something called the CZT. It's the cadmium zinc telluride, and it can detect hard X-rays and gamma rays. So it's a sensor that Garrett designed, and a high voltage power supply that I built on it. And so we're going to be building the next satellite. So most likely you guys would be working on something like, this part has to be on so it can be launched. So you guys don't have to worry about that, like, because you have classes and you need to be focusing on your studies a lot. But there's other projects like the Yagi antenna where multiple people will probably be working on it, and you guys can collaborate and stuff like that. And it's a non-critical thing to be done so that we complete the mission.
What data are you guys getting exactly? Just information about the satellite, or are you getting anything from beam in space?
This is more of a precursor model to the next one that we're building. This particular satellite, because of the accelerated time frame, usually you have over a year to do it, and within 3 months, and I'm really happy but shocked it worked. We actually did all the circuit layout to actually put the CCT array on, but because we do such extensive testing, it's why it probably worked, unlike most other satellites. Because only 10% of CubeSats actually work. Most of them become space junk. So we're like 10%. And then of those 10%, only 10% of those actually complete all their missions, all their goals. So like we're really close. We're at like 95% success. We just have to do the torque coil and we're done. And so that's pretty cool that we're able to do that. I just totally lost my train of thought. Which question?
Just what data are you guys collecting exactly?
Okay. So the data for this particular satellite is the magnetometer data, the temperature, and the 4 solar panels.
Okay.
That's basically it. It's like I said, it's an engineering concept more than anything else. It's the framework for the next satellite. And we, took a lot of experiences from other people's failed designs. For example, one of the things that this has is a Doty circuit, and so we call it Doty circuit. So if the battery gets to a certain level, 3.4 volts, it actually cuts the entire power off to the satellite and doesn't turn on again until it gets to a higher voltage at 3.7, I think I said that. And so what it did was a lot of other satellites, if they get in a weird state in the code, they'll just run the battery all the way down to 0.